In this video lesson, we're going to delve into the quantum chemistry of carbon by looking at the changes in how the electrons are arranged around carbon in order to produce molecular orbitals. Okay, so the first starting point is the ground state of carbon. We know that carbon has 4 valence shells. This is one representation that we've looked at in the past, the Lewis structure for carbon. We've also looked at carbon in the Bohr model, 2 electrons in the first energy level and 4 in the second energy level. These models are simpler versions or views of the atom that help us visualize where the electrons are found in comparison to the nucleus. By looking at the electron configurations, we get a little bit more complete and accurate version of where the electrons are found. We know that in the first energy level in the Bohr model, electrons are found in a 3-dimensional space known as the 1s orbital. We also know that the other 4 electrons are found in the second energy level, where those electrons are found in 2 different places. 2 of them are found in the 2s orbital, which are a little bit closer to the nucleus, and 2 are found, 1 in each of 2 p orbitals, which are a little bit further away from the nucleus and are in a dumbbell shape. These would represent the valence electrons that we've been showing in the Lewis structure for carbon when we draw Lewis structures. We can also show the shorthand version where we only show the electrons in the last energy level, or electrons that the electrons that are found beyond the last noble gases electron configuration, in this case helium. This configuration seems to show that carbon is having the ability to make only 2 bonds because we've only got 2 unpaired electrons. So we know that something else is at play when carbon forms bonds. It's not as simple as the electron configurations lead us to believe. So we know that in order for carbon to make its 4 bonds, it must have 4 unpaired electrons. So at this point, we realize that one of the electrons in the 2s orbitals, which is a sphere, must be promoted to a higher energy level. And keep in mind, the p orbitals are a little bit further out in energy, a little higher in energy, and a little further away from the nucleus. So a change like this isn't a drastic change needed to achieve unpaired electrons, as we see in the Lewis structure. So this partially explains how carbon can make its 4 bonds. The only issue with this view is that carbon would not make 4 equivalent bonds. Unfortunately, in this case, we would have 1 bond would be produced between an s orbital, and the 3 other bonds that are available would have to be produced between p orbitals. And the geometry that we would predict for this molecule containing carbon does not match the geometry of the orbitals that we know exists, especially when there's 4 single bonds to carbon. We know that carbon, when it has 4 single bonds, produces a tetrahedral shape with an angles between them of 109.5, whereas we know the geometry between all of those p orbitals is 90 degrees at best. Okay, and we're not really sure what would happen exactly if you're trying to form a bond with this 2s orbital. So again, this isn't the complete picture. Something else must be at play so that carbon can form 4 equivalent bonds when it makes its molecules that contain carbon. So what has been postulated is that orbitals must be hybridized or mixed. So valence shell orbitals can be mixed in a variety of ways to achieve those molecular geometries that we know exist based on X-ray crystallography and the VSEPR theory. If we need 4 identical orbitals so that they can overlap and form bonds with the orbitals of other atoms, we would need to mix that one s orbital with 3 of the p orbitals together to make 4 new orbitals, all with the same energy level. Okay? As a result, if they all have the same energy level with 1 electron in each, they would be able to make 4 equivalent bonds, all the same length. Those 4 orbitals would arrange themselves as far apart as possible and produce a tetrahedral arrangement we know exists when we have Lewis structures that have codes of 4+, so 4 atoms attached, no lone pairs, 3 atoms attached and 1 lone pair, or 2 atoms attached and 2 lone pairs, we would achieve that tetrahedral arrangement of the orbitals. Now you'll notice that when we mix the p orbitals, they still kind of look like p orbitals, but they are elongated on one end with a smaller lobe on the other. And this is the result of mixing the s orbitals with those p orbitals. If we need 3 identical sites for bonding, we would still mix the s, but with 2 of the p orbitals. That would give us 3 identical orbitals available to arrange themselves in a tetrahedral arrangement, which are 120 degrees from each other, so that we can have 3 atoms attached with no lone pairs or 2 atoms attached with only 1 lone pair. Lastly, we can mix only 2 orbitals together, an s and a p. That would give us 2 identical orbitals here, which could be arranged in a linear relationship with an angle of 180 degrees between the bonds and allow for 2 atoms to be attached with no lone pairs. Now, one thing that I did not mention is the name of these orbitals, because these can be confused a bit. When we mix an s with 3 p's, we give each of these orbitals a name called sp3 hybrid orbitals. Okay? And it's because they mixed 1 s with 3 p's together. If we only mix it with 2 p's, they're going to be called sp2 hybrid orbitals. Okay? So each one of these is an sp2 hybrid. And if we only mix an s with 1 p, these are going to be called sp hybrid orbitals. Okay, so keep all that in mind when we're looking at a few simple structures with carbon. Let's take into account, first of all, methane. So this is just a simple, straightforward structure. Carbon attached to 4 hydrogen atoms. We analyze it using VSEPR theory. We'd say there's 4 atoms attached with 0 lone pairs. It would be a tetrahedral arrangement with 109 degrees between the bonds. How is this achieved? Well, as we mentioned, if I need 4 equivalent spots, I would mix an s with 3 p's, so I get 4 identical orbitals called the sp3 hybridization. Okay, so here carbon arranges its 4 hybrid orbitals around the carbon atom, and hydrogen can attach and share its unpaired electrons by overlapping of orbitals, as we can see here, forming bonds. Okay? So a bond is made between the sp3 hybrid orbital of carbon and hydrogen. Another bond by overlap of these 2 orbitals, the s orbital of hydrogen with the sp3 hybrid orbital of carbon. Same in this bond and same in this bond. We get that tetrahedral arrangement. Now, another little way to kind of illustrate this is by looking at the maybe a kind of a hybrid kind of electron configuration for carbon. Okay, carbon doesn't have an S with 3 P's on their own. They mix them all together to form 4 identical orbitals, all with the same energy, all with 1 electron in it. And they'll form overlaps between their sp3 hybrid orbitals and the 1s orbitals of each of the hydrogens. So a little diagrammatic way to kind of integrate the electron configurations with the picture we see. One additional thing I want to say is if you have this direct overlap between orbitals, we call this a sigma bond, okay, for direct overlap. Okay, now let's look at some multi-atom molecules that we have. Okay, so we have 2 central atoms here. In ethane, again, we analyze the valence, the Vesper theory. This has 4 atoms attached, so the code would be 4 plus 0. It's a tetrahedral arrangement, same with this other carbon as well. If we have 4 plus 0 and it's tetrahedral, we need 4 identical orbitals. This requires sp3 hybridization of the orbitals. Okay, so our carbons, each carbon here has mixed its 4 orbitals together in the valence shell to become 4 identical orbitals, all with the same energy, shown in a similar bank there. Similar to in methane, the hydrogens are going to line up and pair up unpaired electrons through their 1s orbitals. As we've seen before, and produce sigma bonds, which is shown in this diagram here. We got a sigma bond on 3 sigma bonds to hydrogen on each of the carbons. 1, 2, 3 sigma bonds. But then additionally, we have a sigma bond between the 2 carbons, and those are achieved by overlap of each of their sp3 hybrid orbitals. So again, another sigma bond holding these carbons together. Okay, so another way to visualize that. What changes here is when we start having multiple bonds. What exactly happens in that situation? So let's take a look at what happens with ethene. So ethene, we know, has 3 atoms attached, but no lone pairs on each of the central atoms. Okay, so it has a different code. Its Vesper theory shape would be trigonoplanar with an angle of 120 degrees between all the bonds. Trigonoplanar on the first carbon and on the second carbon. Okay, this requires only 3 identical orbitals to be achieved through hybridization. So we mix an S from the carbon with 2 P's of the same carbon in sp2 hybridization of the orbitals. What does this end up looking like? Well, we've got our sp2 hybrid orbitals. Okay, we've got our 1 bond between hydrogen and carbon, forming a sigma bond here between the 1s orbital of hydrogen and the sp2 hybrid orbital of carbon. Same with the second carbon-hydrogen bond. You also see this is true on the other atom as well. And we see that the carbons also must overlap their orbitals to form a bond between the carbons between their sp2 hybrid orbitals. And we can kind of see this visualized here with the electron configurations. Here's the sigma bond between the carbons. Here are the sigma bonds to the hydrogens on each carbon atom. Now, what's left is, because we only mix 3 of those orbitals together, and we only have 3 that are identical, we've left out one of the p orbitals. By doing that, we can achieve a second overlap of orbitals between the p orbitals that are left over in each of the carbons. What do the p orbitals look like? Well, we know they have 2 lobes, okay? And they're going to want to be 90 degrees from any of the other orbitals, and the only way to achieve that is 90 degrees to this plane. If these are all in one plane, these p orbitals are up above and below that plane. Now, they achieve their bonding in a different manner. It isn't a direct overlap like we see with the sigma bond, okay? Rather, it's a sideways overlap, if you want to say that, where these p orbitals, the top lobes can overlap together and the bottom lobes can overlap together. And we have 2 parts of one single bond. So this pink bond, the highlighter is highlighting 2 parts of one bond called a pi bond, okay? The way I kind of think of it as is a sideways overlap. Now, if you're trying to visualize the difference between these 2, I try to think of it in terms of handshakes, okay? This would be like an overlap where you would hold hands in this manner. And just zoom out here just a touch so you can kind of see what I'm talking about. But to achieve this kind of thing, it's almost like you have to, hold together someone's elbow and hand with the other one, so you're overlapping sideways on a bit. Okay, so here's my elbow, here's my hand, and I'm holding here on the top and also in the bottom, if you can see that as well. So it's not nearly as strong, okay, as the direct overlap, but there is some kind of attachment between those 2. So sideways overlap versus direct overlap. So what this tells us basically is a double bond is made up of 2 different types of bonds. A sigma bond, which is that direct overlap, plus a pi bond, which is that sideways overlap. So keep that in mind. When we progress to ethine, we see something slightly different happening as well. We know that something else must be happening because analyzing the Vesper theory, there's only 2 atoms attached, there's no lone pairs, so there's a requirement of having 2 identical spots for bonding and no more. So we only need to mix together an S and a P and undergo sp hybridization. Okay? What does that look like? Well, if I look at the electron configurations, well, the S and the P, they have the same energy. That's why they're locked together. Same on the other carbon. Okay? And then the p orbitals are separated and they're available for bonding as well. Okay? I could actually have had these connected together. I just separated them so you can see the differences there. Okay, so what ends up happening in a bonding diagram? Well, sp hybrids will overlap with each other between the carbons. Okay, that's direct overlap. That's my sigma bond here. The other sp hybrid on each carbon is going to attach to a hydrogen through sigma bonds. And then the 2 carbons here have 2 more bonds that are required. And so that's achieved through 2 overlaps of p orbitals on different carbons. What that produces, just like in the double bond, is a pi bond above and below, 2 parts of one bond. Okay. Just complete this here, just a touch. And then a second pi bond achieved. Remember, p orbitals want to be at 90 degrees to each other, so the s-p hybrids are along one line. This will be vertically up and down. This will also be at 90 degrees to it, so in and out of the page. And we'll have some overlap between those two lobes, and that's represented here as another pi bond. So we end up having a sigma bond between the carbons and and 2 pi bonds. And that allows us to get our triple bond. As you can see, there's quite a bit of bonding occurring around the carbons. We've got one along the bond axis, above and below, and front and back the bond axis.